I posted on the topic while she was giving a news conference on the same topic. I learned a fair amount. And I thought it was interesting, and I thought she should come here and share her information with you guys. So, Allison, the floor is now yours.
Okay, great. Thank you. So I think we're going to turn off some of the lights to stuff. Yeah. Okay, great. So I'm a professor at the University of Kansas, where I have been for about a year and a half. And you guys are my first colloquium this school year, so everything in this talk is brand new. Yay! So you guys get the first chance to ask questions and tell me what's wrong. Okay, so first of all, I would just like to advertise, now that I'm a professor, I don't have time to do my own research anymore. So I have a whole cadre of students whose work you're going to see throughout this talk. And all my students, I should mention, they're all doing like really great work. My graduate students are all first and second years, and I just got a postdoc this year, and my undergrads are all juniors and seniors. All right, so let's start with, I guess, probably the most famous picture of the galaxy in recent history. This is, of course, M87, and we're going to be talking about the effect of black holes on their galaxies. Not this particular galaxy, but I think it's always useful to start with the scales of what we're looking at, because it gets really easy when we start talking about the energy output of these black holes to forget the physical scales of what's happening. And so this galaxy is, of course, an older galaxy. It's all bulge dominated, meaning that any star-forming disk has long been destroyed. Every point that you're seeing there, all that fuzzy light, that's a star, and all those stars are moving randomly about the center. And the size of this galaxy, like roughly, we want to say that it's like 100,000 light years across. And I am so sorry for using light years. I looked this up for a public talk, and I never converted it back to a unit that we use. So we can do that in our heads, I guess, and get parsecs. It's probably a few kiloparsecs. Okay. So then at the very center of this galaxy, of course, is a black hole, and probably our most famous black hole now. And this is a supermassive black hole. It's 1 billion times the mass of the sun. And this picture is particularly nice because it shows us the scale. This black hole is the size of the solar system, essentially. So we want to think about galaxies are 100,000 light years across, and our solar system is like less than a light year. So we're talking about at least 5 orders of magnitude in difference in size. And yet, when we compare the properties of black holes, specifically the mass is usually what we're most interested in, with galaxies, we get the well-known relationship that black holes are tightly correlated with the mass of their host galaxies, specifically the bulge mass. So that the larger the mass of stars in your galaxy, the larger your black hole mass. And this has led to some interesting assumptions. One assumption being that this relationship that we see for local galaxies is evidence of a causal relationship. So that is that black holes are affecting their host galaxy. And again, when you see this nice tightly correlated data that holds for lots and lots of galaxies, it's easy to think, yes, this must be true. Remember, we're talking about 5 orders of magnitude. And so what that would look like just in a normal disk galaxy, this is just a simulation of a disk galaxy. So this would be your accretion disk around your AGN or your black hole. It's starting to heat up. And suddenly you have this outpouring of energy and winds and jets of radiation, and it needs to, if there's going to be some kind of relationship, some causal relationship, it needs to sweep through that entire host galaxy. And so when we start to think about things on this scale, it becomes more of a question of really? Is this really what's happening and driving the relationship? And in some cases, we think that it definitely is. So we definitely can see these kinds of relationships develop. And so one of the most common places that we see that is in mergers, all right, major mergers in particular. We see two galaxies collide, two big disk galaxies collide, and tidal tails get strung out. This is the gas view. The gas is starting to heat up. As this gas is being compressed through shocks in different regions of the galaxy, you get a huge burst of star formation, and then the galaxies start to coalesce again. Each one of these galaxies will have a very active supermassive black hole at this point in time. They will be fueling gas onto their supermassive black hole. And then the galaxies will coalesce, you'll get a final burst of star formation, and then your black hole will really light up, and you will enter the quasar phase, which is the most active phase of a galaxy's life. And then that gas gets dispersed, and you are left with your elliptical galaxy. So just in pictures, this is what this looks like for mergers. And it has to be galaxies of the same size. We don't think that minor mergers do this, okay? And so you will go through, so it's thought to be, simulations can show like a linear process. You merge in galaxies, followed by a burst of star formation, where your star formation is like 1,000 solar masses a year, followed by an obscured quasar phase. And I am using quasar to mean like the most active phase of black hole growth. So this is when your accretion disk and your material around your black hole is the most luminous it's ever going to be. And it's obscured because you have funneled all of this material onto the center, and then your winds from your quasar are able to disperse this material, and then you're left with an early type galaxy. Okay, there's some problems with this picture though. Okay, the first problem is that there's no smoking gun for AGN feedback in galaxies outside of the radio loud population. So this is a radio loud AGN, and here we absolutely see these jets of material being flung out of the galaxy, but the out is the key part, and they're heating the circumgalactic medium. But within galaxies themselves, we do see some evidence for winds in individual objects, but there is no broad universal picture. Also, because of the timescales that this happens on, we can't actually see a wind originate like in that movie and watch it sweep out gas and dust. So all we can do is kind of look for winds and calculate the mass outflow rate and see what it would do. And it turns out it doesn't do a whole lot for most galaxies. Okay, so that's one problem. The next problem is that AGN go through activity cycles. So you don't always have a very active black hole. Sometimes it's not doing anything, much like the Milky Way's black hole. Like we think our black hole is more active in the past. And so that makes it very hard to correlate with the life cycle of a galaxy, because you're only able to trace star formation in galaxies over 10 million or 100 million year timescales. You can't get down to an instantaneous star formation rate. But you only see the black hole accretion on instantaneous terms. So how can you possibly relate something that's instantaneous to something that you can only measure on 100 million year timescales? All right, and then the other problem is that there's multiple types of AGN. So this one is an example of a low luminosity AGN. So you have the most active AGN here on the right, the radio loud population. They're only about 10% of all quasars. And then on the left, you have low ionization AGN that live in disk galaxies. And so is there one common picture of growth for both of these types of objects? So how can we get at this broad picture of how AGN fit into galaxy evolution with these kinds of problems? So first, we can beat down this whole idea of AGN going through activity cycles by using population statistics. And so that's what I'll talk about first, is looking at large populations. And then to talk about AGN feedback, we really need to look for the extreme cases, because those are the cases that we think are powerful enough to incite feedback in their host galaxies, and so we need to look at those and see what they're doing. All right, so first I am going to talk about population statistics. And the ideal, if you're going to do a large population survey, there's an ideal place to look in the universe. It's not today, and that's because there's not a lot of AGN activity today. So This is the history of the universe. I don't know, you probably see this a lot in colloquium. We play like colloquium bingo, cross off this picture. Yeah, so, okay, so everyone's, no need to introduce this. But the most active period for black hole growth and for star formation, so for galaxy coevolution, is about 3 to 6 billion years after the Big Bang. So we have, before then, we have cosmic dawn, where galaxies are starting to form, they're starting to form their stars, the black holes in the center are starting to emit a mass. And then we have cosmic noon, where galaxies are slamming into each other and fueling big bursts of star formation, and their black holes are growing. It's the peak epoch of activity. And then after that, we have where we are, and things are winding down, and it's more like cosmic happy hour as we enter the twilight of our universe. So as we look back at this epoch, what we want to know is how many galaxies are hosting actively growing black holes, okay? So every massive galaxy has a black hole. They're probably already in place at this point in time. So we don't really care about that. What we want to know is how many are actively accreting material and how much material are they accreting. So this is a Hubble image of the of good south. So all the galaxies you're seeing here are basically existing in this epoch of cosmic noon, roughly speaking. And you can even, just looking at this picture, you can notice some things about the galaxies. So we have blue and red galaxies. We have some galaxies with clear spiral structure, and we have some galaxies that are fuzzy blobs. So already, by this point in the universe's history, galaxies have evolved to take on distinct shapes. And what role do black holes play in that? So this is the Chandra view of that same field. So Chandra is an X-ray telescope. So now every dot you're seeing there is a supermassive black hole that is actively accreting material, okay? So this is the most surefire way to go find supermassive black holes in the distant universe, because only the accretion onto black holes basically has enough energy to excite this amount of X-rays. And so when you see a very luminous X-ray source, it signals growth of the black hole. Okay. All right, there's a problem here, and that is that in the distant universe, there's a lot more gas around, there's a lot more star formation, and what that means is that there's a lot more dust around. Dust makes everything a lot harder. So we can watch a video of what dust does to a galaxy when you dump it on. So this right there, this is our ideal way to look for AGN. You are seeing an X-ray source. You can see it in both the soft and the hard X-rays, and crucially, you're also seeing a lot of mid-IR. This is due to the dust that surrounds the AGN that it is responsible for heating, and you can also see the accretion disk. Okay, so this is peak observations for AGN. We can see it in every wavelength regime. When you dump dust onto it, all that emission goes away. So we can watch that again. So you can watch your AGN grow in luminosity, and then we dump some dust. Okay, as we dump dust onto our galaxy, in the optical, it looks just like a normal galaxy anymore. You will miss your AGN completely if you look in that wavelength regime. You can see it still in the hard X-rays. The problem here becomes it takes much, much more time to be able to see it. And time is money. And so basically, the big limiting factor in everything that we know about the universe is money. Do we have enough money to look for it? And so we don't for a lot of these AGN, but you can still see them in the mid-infrared. Okay, so the mid-infrared becomes a very good place to identify AGN candidates, but there's some tricks to it, because even in the mid-infrared, things aren't perfect. Remember, these galaxies in this earlier universe have a lot of star formation going on. Star formation emits very strongly in the infrared when you have a lot of dust in your galaxy. So these are templates of what emission in galaxies at redshifts of 1 to 2 look like. The picture does not correspond to that. I'm not going to show you pictures of 1 to 2 galaxies because they don't look like anything. So this is just, if we had, again, infinite money, this is what we think the galaxies would look like. Okay, you still have these nice spiral galaxies that are forming stars that have a lot of dust in them. And from the near infrared all the way to the far infrared, the emission is dominated by stars. In the near infrared, around 1 microns, you get emission from the old stellar population. Around 10 microns, you get these spiky features that are polycyclic aromatic hydrocarbons, and so those come from regions directly around newly formed stars. And then in the far infrared, around 100 microns, you have this peak of cold dust, and cold in this case is 25 Kelvin. And this dust comes from further out in the galaxy and more like the spiral star, the arms, or the interstellar medium. But it is still heated by photons leaking out of star-forming regions. When you have a growing black hole at the center, you don't see any of that. Instead, you see this pure power law. And it's not because your host galaxy isn't there anymore. It's because the dust around the AGN is so hot that it can outshine the rest of the galaxy. But we still know that this host galaxy is here because around 100 microns, you still see a lot of emission. That emission is still cold dust from your host galaxy. So this galaxy still has a lot of star formation in it. If star formation was depleted, you would see that emission around 100 microns start to fade. Okay, so these are 2 clear-cut cases. Unfortunately, the AGN here, this type of galaxy that has this type of emission is also easy to detect in the X-ray. It's typically an unobscured AGN. When you get obscured AGN, it looks a lot different because everything becomes harder. Instead, you get this nice mix of both your AGN and your star-forming galaxies. You can see like a power law, and you can see these spiky features, but you see a lot of cold dust as well. And so I call these composite galaxies. And composite galaxies are really easy to misidentify as star-forming galaxies, basically due to the coverage that we have for telescopes. So for example, for Spitzer, you'd only get like a band here and a band here, and so you'd have to base your whole characterization of a galaxy on a couple different photometric points. So it becomes really hard to do. James Webb is going to help identify more sensitively hidden AGN in the mid-infrared. So this obscuration changes with how you are looking at your accretion disk. So you have your black hole, you have the broad line region around your black hole, that's the BLR, that's all this gas clouds moving close to the speed of light, and you have your accretion disk. If you are looking above the torus, or even through the bottom of the torus, you will get X-ray bright AGN, and you see a very specific shape to your infrared power law. Okay, so that's the infrared emission, but they will also be detected in the X-ray. If you are looking directly through the dust, you will not see the X-rays, and not only that, when you only have a couple of data points, that infrared emission is mistaken for star formation because it looks a lot like star formation. So only very, very few of these kind of composite galaxies are actually detected in the X-ray, and so that means that our understanding of AGN growth in the distant universe could be biased because it's really hard to see these things. All right, so what can we do to combat that? Currently, with the facilities we have available, we can do nothing, but there were some space telescopes prior to right now that were helpful for this, and there will be again. So we can use color identification to select these galaxies that we think are hiding growing black holes in them that we're currently missing. And the way that we do that is by tracing the full infrared spectral energy distribution. So on the left are models. These models show how your infrared emission changes as your black hole grows more luminous. On the right are real galaxies. in color space, so these are all galaxies at redshifts of 1 to 3, and the colors here are 8 or 3.6 microns. These were two Spitzer bands. Sorry, these were two Spitzer bands. Spitzer's no longer with us. That basically they trace the shape of, do you have emission from old stars, or are we seeing this hot dust emission? Okay, these colors by themselves, again, only really pick out X-ray luminous AGN. So we can add to that Herschel. So again, Herschel no longer with us, but we can combine Herschel with Spitzer to trace the amount of cold dust. And it's this amount of cold dust that will change as your AGN begins to heat up. So that star-forming galaxies live down here. They have lots and lots of cold dust, very low mid-infrared emission. X-ray luminous AGN live up here. They're hot all over. And then your composites live in the middle. So one of the open questions has been, we're kind of identifying these candidates of things that I think have AGN in them, but there's a lot of scatter. And so is it true? Does this little bit of mid-infrared heating, does it really signify that there is a buried AGN at the center? Okay. Because if we can prove this, then we will prove how ubiquitous AGN-R and black hole growth is in the more distant universe. So what my student has been working on is taking the cosmos field, which is a 2 square degree field that has, you know, HST and Spitzer and Herschel and Chandra observations. And she has used infrared colors to identify thousands of AGN candidates. And so now we need to confirm them. They have a little bit of excess mid-infrared emission, but they don't have any X-ray emission. So what are we going to do about that? To confirm an AGN, you really need an X-ray detection. So we can stack. So that's what we've done. So we've stacked Chandra data. So you go and you cut out the little piece of the Chandra sky and you stack it with lots and lots of other galaxies, and you get an average X-ray emission for galaxies that were not detected in the first place. So it doesn't allow us to say anything individually. That's okay. It allows us to say something about the population. And what we have found is that even the tiniest little bit of mid-infrared excess emission, which is what is plotted on the x-axis of the left plot, is the fraction of mid-infrared emission that we think is due to an AGN. Even the tiniest little bit actually does reliably signal an AGN. All of these galaxies have X-ray luminosities above the green line, which is the threshold for saying that you have an AGN. And inside each one of these stacks are thousands of galaxies. So we now have about 5,000 galaxies that we believe were never identified before because they're missing from the X-ray catalogs, but we think that they do have X-ray growth in them. And then the same thing on the right, we've plotted AGN infrared luminosity versus their X-ray luminosity, and all of our stacks are consistent with the AGN infrared luminosity of X-ray detected galaxies. So even though they were X-ray undetected, they had the same amount of dust heating as the X-ray detected galaxies. But now we're pushing down to lower thresholds, and we're starting to detect galaxies just as their AGN lights up. And so this allows us to do something pretty interesting. So again, it's an average over thousands of galaxies. And so the next slide is pretty preliminary. But this is the main sequence. All right, so let me tell you what you're seeing. On the bottom axis is stellar mass, and on the y-axis is star formation rate. Galaxies that are growing at a normal rate, undergoing secular star formation for long periods of time, have a well-known correlation between their star formation rate and their stellar mass, and this is called the main sequence, and it's plotted as one of the colored lines in different redshift bins. So we can see where our X-ray AGN growth is occurring. And all of our stacks, except for the brightest ones, lie on the main sequence, indicating that most of this black hole growth is occurring while galaxies are building up their stellar mass. So except again for the highest spin, the very bright AGN seem to be falling below the main sequence, but I'm less convinced about that. For the most part, things that host obscured, undetected AGN are consistent with star-forming galaxies. And so what we want to do next is hopefully use this kind of thing to answer an open question, which is, how does quenching occur? So these two plots show the exact same thing, by the way. The plot on the right is just a nice visual way to look at the plot on the left. So what we think that one paradigm of quenching, of how galaxies end their life, is that they start out in the blue regime. They're nice extended disks, and they have star formation all throughout their galaxy, and then they compactify. They get smaller first. So the star formation quenches in the outskirts, and then the star formation quenches all over, and they move up into the red regime. So they become very like small things that aren't forming stars anymore. So that's the general picture. What the paper on the left, it's one picture, by the way, it's just one. What the paper on the left found is that X-ray luminous AGN at redshifts of 1 to 2 actually live in a very special regime. They live right here where galaxies are starting to compactify. So when your galaxy starts to compactify, it feeds your AGN growth, and then your galaxy moves up and quenches. So now we think we found the precursors to this. And so our hypothesis, we haven't actually measured this yet, this is our next step, is to look where our X-ray undetected AGN lie in this diagram, and to see if the populations match, that these X-ray undetected AGN could do most of their growth while your galaxy is forming most of its stars prior to quenching. Okay, and so this would tell us basically that the majority of black hole growth occurs prior to quenching in large populations. This becomes really important for what's next. So now I'm going to leave population statistics and talk about extreme things. The extreme side of things is that that's not true at all, is that once you have a luminous AGN, it is responsible for quenching your galaxy, and that AGN growth comes after stellar growth. This is kind of in the canonical picture. You have your stellar growth, then you have your AGN growth, then you have this blowout period, which is what the diagram up here is showing. And so to prove that that's the case, you need to go searching for feedback. Unfortunately, feedback is really, really hard to find. So the plot on the right shows measurements made in a whole bunch of local galaxies of molecular winds and ionized winds. So we know that growing black holes can drive winds. They can drive molecular winds, they can drive ionized winds. Does that matter? No, not really, not according to this plot. Because if you look at the mass outflow rates, it's really only enough to quench a galaxy when it's above the 10 or maybe 100 mark. So only in a few cases are you really driving enough outflow to dispel your entire interstellar medium. So if we want to understand, are extreme AGN quenching their galaxies, we need to go find extreme AGN. Finding extreme AGN is very different than finding the bulk of AGN growth. The bulk of AGN growth requires population statistics in normal galaxies. Extreme AGN requires a large area survey, because these will be the brightest things in the night sky. And so to find the brightest things, you need to look over a very wide area. And so we have this area in the Stripe 82 region that's 16 square degrees, where we have both X-ray and infrared detections. Infrared becomes necessary because if you want to look at the host galaxy properties, you're going to need infrared, because your X-ray source is going to outshine you in every other wavelength. So from this 16-degree square area, we have almost 3,000 X-ray sources. From these 3,000 X-ray sources, we have 800 that are bona fide, unobscured quasars, and so their X-ray luminosity is above 10 to the 44, and they're unobscured based on their optical emission. We also have 120 sources of the entire 16 square degrees. We only have 120 sources that have both an X-ray and an infrared detection, because X-ray bright sources are typically not infrared bright sources. Okay, so below 10 to the 44 ergs per second in the X-ray, I'm going to call that, for lack of a better word, a star-forming galaxy for the purposes of this, and the quasars are everything above 10 to the 44. We also, just due to population statistics, don't really look at evolution with redshift, just because I don't have enough to reliably do that. All right, so let's return to this picture and talk about why it's important to look for infrared and X-ray together. So this picture says that you have a dust-obscured red quasar, and then you have this blowout phase, and you are left with a blue quasar. And so you should not see blue quasars with lots of dust. That's the hypothesis, okay? But we've never actually seen this transition from a red quasar to a blue quasar. Again, presumably it happens on very long timescales, so you can't watch that. And so I found a whole bunch of really interesting objects in this survey. Again, 16 square degrees of the sky, and I found 23 really interesting objects. So you have to look over large areas. These are the cold quasars. These are optically blue quasars. They're unobscured, they're very luminous, but they have a lot of cold dust in them. They have enough dust that if you looked at them in the infrared, you would classify them as purely a star-forming galaxy. You would not see an AGN at all. So to walk you through that, what that looks like, so this is one of our blue quasars. It's got an X-ray luminosity of 10 to the 46, so this is really bright. For those of you who do quasars, this is a bright source. This is at a redshift of again, sorry, I wrote this for a different audience, so I wrote down the look back time. The redshift is, I believe, 0.6. I don't know. Okay. So what you are seeing here, this blue light, is all light coming from the accretion disk right around the black hole, or material nearby that has been heated by this. You are not seeing the host galaxy in this image. And yet, when we observe this with Herschel, we see this bright dot here. And this galaxy has 100 times more dust than the Milky Way. This bright dot is, again, that 25 Kelvin dust that must be coming from the host and not the AGN, and I will show you why in just a second. Okay, so this is just one example of our 23. These galaxies really do have a lot of dust, and they really are different from normal quasars. So this is infrared luminosity, or X-ray luminosity. X-ray luminosity versus our mid-infrared data point. So W3 is WISE3, so it's a mid-infrared data point, and to the right is more dust. So our star-forming galaxies typically have lots more dust. Our unobscured quasars, which are the orange points, typically don't have very much dust at all, and our cold quasars have a lot. They have quite a bit of dust, more than you would expect, given their X-ray luminosity. And they are definitely not obscured. Okay, so this is our relationship between 6 micron, again 6 microns is a mid-infrared data point, and X-ray luminosity. Obscured AGN have lots and lots of 6 micron emission because they have lots of dust, and they have very low X-ray emission because the X-ray emission is being absorbed. Our cold quasars do not. They are, for those of you who are entrenched in the AGN community, our cold quasars look exactly like red quasars and exactly like hot dogs. Yeah, hot dogs. Hot dogs are like the brightest, hottest AGN around, but they don't have any cold dust. So none of those other populations have cold dust, and these do. Okay, so that tells us that this cold dust is definitely coming from outside the AGN zone. It has to be further out. And so we can use this cold dust to look at some other properties of the host galaxy and ask what's happening in these hosts. So first, we can look at the main sequence again. So again, this is that relationship between star formation rate and stellar mass. And this is just the cold quasars on it. The 3 different lines are because the main sequence evolves with redshift. And so these are the main sequence lines for like 0.5, 1, and 1.5, because that's the redshift range of my sources. And they are all well above the main sequence. They all have star formation rates of 1,000 or more, a lot of them do. And we can look at where we would expect other sources to lie on here. Submillimeter galaxies, which are the most actively star forming in the universe, lie where that black star lies, whereas AGN, typically unobscured or obscured AGN, lie on the main sequence or below, which is what we had found in our previous research. So these things are the brightest AGN, but they definitely look like the brightest star-forming galaxies. They also, we can calculate, because we know their dust mass, we can calculate their gas depletion timescale. That's how fast are they going to eat through their material. Okay? So our cold quasars are definitely eating through their interstellar medium much faster than star-forming galaxies. They are consuming their interstellar medium at a rate of 6 times faster. And this is just talking about how fast star formation is consuming the gas. If the AGN is contributing, if it is blowing out your interstellar medium, then that would make their gas depletion timescale go down even further. So these things, on average, have a gas depletion timescale of 100 million years. So that's about how much longer they can live. That's an upper limit. Okay, but this led us to, so these are some weird properties of quasars, and this led us to wonder, though, what is the average expected star formation rate of quasars? Because there's very little in the literature to compare it to, because again, quasars typically outshine their host galaxy, and it becomes very hard to measure their star formation rates. So, are these things, how abnormal are these things? So again, we were able to use our Stripe 82 survey to do that. So we have our normal star-forming galaxies that we can measure the star formation rate in, these nice disk galaxies, but we also have a whole population of unobscured quasars that aren't detected with Herschel, because again, that's what you expect, so what can we do about that? So to get at the expected star formation rate of your typical unobscured quasar, we're again gonna have to use stacking. This time, though, we're not going to have to stack the infrared or the X-ray. We're going to stack the infrared. So this is our Herschel image. The one on the right is a star-forming galaxy. So you can see that you actually do detect it in Herschel. Over here, this is an unobscured quasar. There is actually a tiny little dot here, but it's not above the level of the noise. Okay? So instead, we can cut out all of those 800 galaxies that we know are X-ray unobscured quasars, and we can stack them together, and we can get the infrared emission. So this is what my graduate student, Brandon Coleman, has been doing. And so now you're seeing an infrared spectral energy distribution of a stack of hundreds of unobscured quasars. Okay, so it's the 3 WISE data points and then the 3 Herschel data points. These are all stacks. So again, we don't know individually what each one is doing, but we can say on the whole, this actually looks like your expected infrared luminous AGN emission, even though we can't detect these individually. And we can measure their star formation rates, and so that's what's shown on the right. So now we've correlated star formation rate with AGN volumetric luminosity. And all of our stacks are right here. They actually have fairly high star formation rates. Their star formation rates are 100, or maybe a little bit above that. So they are essentially like just below the detection threshold. And all of our cold quasars are still 4 to 7 times elevated. The yellow points are actually a nice confirmation of our results. These are very similar technique, stacking the X-ray, but this time, or stacking the infrared, but this time for optically selected quasars, where we had chosen X-ray quasars. This was work done by Flora Stanley. So what this shows is when you are able to beat down the noise in the infrared, unobscured quasars actually have quite high star formation rates, like unexpectedly high star formation rates. So this picture that the luminous AGN growth follows star formation in a host galaxy, it may not be correct. And one other final thing that we can do with this sample, because we have such good data with it, is we can measure how the black holes and the stars are growing at the same time. So just to remind you, this was our picture, that every galaxy should wind up on this relationship eventually. And so for our galaxies, we have spectra. We have SDSS spectra, which isn't the best, but also isn't the worst. So we can use SDSS spectra for some of our galaxies to directly measure the black hole mass and the black hole growth. So this is work done by my undergraduate, actually. And so he has measured the black hole mass for a lot of our cold quasars, and interestingly, he's found a few weirdos that have this nice O3 blue wing here. That's indicative of an outflow in these galaxies. So this would be feedback in action in these galaxies that we can go then propose for better quality data and do more work with. Okay, and so in our galaxies, in the sample that he was able to work with, he worked with the entire Herschel detected sample and found the ones that he could measure the black hole rate, the black hole growth in. The cold quasars are all the pink galaxies, basically, all the highest volumetric luminosity, and he was able to find, unsurprisingly, that volumetric luminosity actually correlates pretty tightly with black hole mass in these galaxies. So the larger the black hole, the larger your volumetric luminosity. Volumetric luminosity corresponds directly to your accretion rate. So all of our cold quasars are growing at above 10% of their Eddington accretion rate. So they're growing pretty fast. So what does that tell us about star formation? So this was a large sample of galaxies. To measure, to get more accurate star formation rates, we needed actually more infrared data because our coverage of the infrared SCD isn't great for measuring star formation for reasons I can talk about in detail in the question section, but it gives us like a loose handle on star formation, but not super precise for every galaxy. So we used SOFIA to go look at quasars. And so this is one of them. This is the second most distant object detected with SOFIA that's not lensed. This is one of our cold quasars in the Sloan Digital Sky Survey in the middle image, and then on the left is our SOFIA image, or right is our SOFIA image. So SOFIA isn't awesome. We need another far infrared telescope, ideally in space. Because that's about as good as you can get with SOFIA, and this is about the limits of where you can push the infrared, and we proposed for several objects, and only one was actually detected. So this is like state-of-the-art SOFIA for extragalactic stuff. Okay, so because we have SOFIA in this, so this is, if you're not familiar with the wavelength regime that SOFIA covers, it covers all the mid-infrared and the far infrared. So this image is actually at 80 microns. So it's right at like the peak of the transition between the warm and the cold dust. It's why we needed it to be able to robustly pin down the star formation rate. So we combined the SOFIA point with our Herschel points and our WISE points, and we were able to more robustly model the infrared and figure out precisely the star formation rate. We were also able to get out a stellar mass for this galaxy, and with that, we can actually figure out how this galaxy is growing. So this is our little cold quasar, and this is stellar mass versus black hole mass. And we know the black hole accretion rate, and we know the star formation rate. This guy is growing at 10% Eddington. So we can plot the flow of what's going to happen to this galaxy and how it's going to evolve over time. This galaxy is pretty unique, pretty unexpected, because its star formation and its stellar mass, or its star formation and its black hole, are growing at exactly the same rate. They are increasing the mass at exactly the same rate, which indicates coevolution, very high coevolution. Its star formation rate is 1,000. No, it's not. It's a little bit too high. It's a few hundred, and its black hole mass is almost 10 to the 8. No, 7.5. It's right there. Okay, and so it's growing. It's building them both up coevally, and this kind of measurement's really hard to do because you have to be able to see everything and measure everything, and so it's only been done in a handful of other galaxies, which we also plot up here to show you just in general how galaxies tend to flow. And there's not one typical flow pattern, but the cold quasars are definitely this one. It's coeval, and so we think that the rest of them are too, probably, because that's what we do in astronomy. We make broad generalizations from one galaxy, and that's all you have. Okay, and so with that, I will leave you with my conclusions, which is that if you want a full picture of AGN growth, you need to look at both population statistics and the extreme cases. You need to be looking at both of them. Population statistics indicate that there is a lot of undetected AGN growth that current surveys have been missing if you're just looking for X-ray AGN, and this buildup occurs behind dust and it occurs on the main sequence, whereas the extreme cases show that they also have a lot of star formation, a surprising amount of star formation that is contradictory to some current hypotheses about how galaxies evolve. And so that's it. All right, James Webb is going to help. That's all I did. Okay, yeah.
In your previous slide,
Yeah.
for all the other galaxies, what's the significance of the layer after the dot? I don't understand.
Oh, the arrow shows how they're growing. Because you can measure the growth rate, you can measure how fast stellar mass is increasing and how fast black hole mass is increasing. So it shows if this were to occur, like keep going for over a gig a year, this is how your point would move.
That's growing unusually fast.
No, we just made the arrow bigger so you can see it better. The length of the arrow should not be used to infer anything. Yes.
So, why didn't you use the radio to find the X-ray obscured galaxy?
Oh, so we did. There's just not that much radio data. So this would be the first survey, and we've looked, and it wasn't. First of all, I believe it wasn't a super deep survey, but I might be misquoting that. But only like 3 of our galaxies are actually detected in the radio. Some of them are not in the radio.
What's the declination? Right.
It's like +1 to -1.
Yeah, I think you'd have a very good VLA survey of that.
They're not in there, but it's the first radio survey. It's what it's called. It's a new survey.
That's a specific survey.
Yes.
It's not very deep, you're right.
Okay. Yes.
How can you measure the arrows of where these things are changing on individual galaxies?
So this one, you actually can't, I don't know if you could do it statistically. I think the only way to do it is individually.
How do you do
So the way that you do it is that you have to measure the black hole mass by modeling one of the emission lines. And then you can get the accretion rate if you assume that the X-ray luminosity is the accretion rate. And then you get the star formation rate, and you assume that your stellar mass is correct, which is a big assumption.
you assume that your stellar mass
Is correct. Yeah, it's really hard to measure stellar mass because, especially in luminous things, because you also have an accretion disk there.
But how do you get the rate at which the star formation
Oh, it's okay. It's the specific star formation rate. So it is the star formation rate divided by the stellar mass, and then you normalize the black hole accretion rate by the black hole mass, and that's what the arrow is. It's the rate of change in the mass.
Now, well, I can see how you can get the rate of black hole mass change by the accretion.
Right.
But I'm not understanding how you get the rate of the star formation.
Right. So you take the stellar mass, and you assume, like for a giga year, if your star formation rate stays the same, this is how much your stellar mass will increase.
You're just saying how much the mass will increase,
Yeah.
not how much.
Yeah, I'm not saying the rate of change of the accretion or that. Yes, it's a rate of change of mass. Yeah.
So, for a lot of these sources that are on the redshift like 1 and 3, but yeah, you definitely get observation affecting your X-rays, but that observation it becomes less so as you go higher redshift, right? Because your pump starts to transition into your younger bandpass.
Yes.
So how, I guess, you know, given the deficit of X-ray sources that you're seeing, are there estimates for what kind of palm densities you're looking at are required to do that, or does that pump get less severe for the higher redshift sources? Is there an excess of sources at higher redshift that would indicate that you're getting those higher energy, restoring higher energy components being essentially redshifted into your soft X-rays?
Right. Okay, so that's a really good question. Coming up with, we haven't actually used the X-ray to estimate column density yet, because to do it properly requires modeling the X-ray. We don't have enough data to do that. We can also look at hardness ratios of soft to hard, and we just haven't done it yet.
Yeah, it just seems to me like, I mean, you have a pretty consistent flux limit for that heat field sound, right?
Yes.
So it seems to me like if you have sort of a typical AGM power law spectrum with maybe some additional ones, that you'd be able to estimate that just based on and the statistics of the sources that you do see.
Yes, so that's a really good idea. Haven't done it. But the stats that I showed were actually for Cosmos.
Okay.
So they are not as deep as that for the Good South, because we've done this analysis in Good South too, and the results are a lot weirder because again, the Good South is so deep that you're really not missing a whole lot. But yes, I will email you about that. That's a good idea. Yeah.
I wonder, just don't possess this particular knowledge. How do you measure the volumetric luminosity? Isn't that the integrated luminosity overall?
Yeah.
How do you measure it?
We love conversion factors. So it's assumed basically that your X-ray luminosity is about 10% of your volumetric luminosity.
Oh, I see.
So that's the typical relationship.
It's just the X-ray scale, right?
Mm-hmm. Yeah.
I wonder if you can comment on possible differences in the dust populations that you're actually detecting.
Yeah.
Would be a factor here.
Yeah, that is a great question. So for all of the galaxies I've showed here, we don't assume that the dust population changes that much because I've set a mass threshold so that we don't have to worry too much about metallicity changes. As you push down to lower masses, so this is going to be a problem with James Webb because James Webb is going to probe much lower masses at these redshifts. Your metallicity changes, and so your dust emission properties are going to change. That's going to make it harder to select out your AGN because as your dust changes, they begin to mimic AGN. The real key regime is actually around 5 microns, where even there, if you take 5 microns and you combine it with like an 8 micron data point, you will still see enough of a difference in an AGN than you will with a lower metallicity galaxy. But you have to be really careful about what colors you're going to probe. But it's only a real concern below about mass of 10 to the 10, but definitely below a stellar mass of 10 to the 9. But for the most extreme things, it's not a concern. Yeah.
Yeah, I'm curious about the stacking process you're using. So are you doing any kind of correction on the background node?
On the what?
On the background node?
Yes.
Image?
Yes. The background is being removed. We're using, do you do X-ray stacking? So we're using a well-known tool that's called C-Stack that's publicly available. But it does a statistical background subtraction, and then we do like a bootstrapping to make sure we really have a signal. Yeah.
So in that X-ray stacking, most of the images you're not actually getting a photon
Yeah.
from the
That's right.
From the radar or
Uh-huh.
galaxy, whatever you call it. And so, are you also keeping track of like the sort of Poisson type statistics
Yes.
to make sure you're not
Exactly. That's how the bootstrapping can help with that, because you want to make sure that you really do have
so like a few outliers not dominating this?
yeah. Exactly.
And also, do you like have you divide? So in the bootstrapping, are you dividing it up into separate subsections or separate samples that you can then say, yes, it does look like it's pretty much random this exposure versus that exposure, and that
Yes.
kind of stuff.
Mhm. Yes, so we used that, and we've done this in the infrared as well, to basically decide the ideal bin size of how many galaxies we need to include in a stack to make sure that our detection that we're getting is a robust detection rather than just a random fluctuation.
But it's kind of weird that a lot of the galaxies never give you a photon.
I know. Yeah.
Unknown caller.
Yeah.
I was just wondering, one of the plots you showed a plot of our right there, and you said, there is something there, but it's not above the noise, what we detected. So how did you detect it?
We stacked it.
Oh, we didn't detect it. This one is not detected.
Oh, that.
It's not detected. It's we then stack it to bring out the galaxy, get an average.
That would have
You
gone
say there
into.
is something there.
This would have gone into the stack.
But how do you know there is something?
Well, it's just supposed to be like illustrative of like if you take a whole bunch of these images and you stack them together, you will get something.
I see.
Like there's still information in this picture.
You actually do know by sort of co-adding.
Yes, it's co-adding. There's something there.
That
Mhm.
there is something there.
Oh, if there are no further questions, let's thank our speaker.